All right. So it's a great pleasure to introduce Professor Masashi Sugiyama, who's the director of RIKEN AIP, who's a well-known member of the machine learning community. He's a leading expert on machine learning. And I would like to also personally thank for his initiative in making this particular EPFL, CIS and RIKEN AIP joint talk series possible. Today, Masashi is going to talk about robust machine learning. And I'm really looking forward to his talk. Without further ado, Masashi, please take it away.
So thanks for the introduction. So I'm Masashi Sugiyama. So I will be talking about robust machine learning for reliable deployment today. So because I'm director of the center, so let me briefly introduce our center in the first page. So our center is called RIKEN Center for Advanced Intelligence Project, so RIKEN AIP. So it's a 10-year national project in Japan, so started in 2016. And we have actually 5 missions. So to develop next generation AI technology and to accelerate scientific research and to solve socially critical problems and to study ethical, legal, and social issues of AI. Then finally, to develop human resources in AI. So we have nice office in the center of Tokyo and also nice room like this. And also we have separate distributed office across the country. Then, so I'm a director, but also I'm a team leader, and my team is in this area, so develop next generation AI technology. And my team is called Imperfect Information Learning Team. And we try to develop novel machine learning theories and algorithms that enable accurate learning from limited information. So let me briefly introduce my team here. So my team has several members, and the most important member is Learnir. So he's basically the team leader, essentially. So he's a research scientist and working on broad area of learning theory. So he's really an expert. Then But Tankarat, so he's a postdoc working on reinforcement learning. And Shuo Chen, so he's a postdoc working on metric learning. Then Jinfen Zhang, so he's working on adversarial learning. Then finally, Jiaqi Liu, so she actually joined very recently. So she's working on weekly supervised learning. And in addition to these regular members, actually we have many great visiting scientists or junior research associates or part-time students and also internship students over the world. So in a sense, our team is quite big. We have a lot of temporary members. So okay, today's topic is about robust machine learning. So in real-world applications, it becomes increasingly important to consider some kind of robustness against various factors, various uncertainties. For example, data bias is quite important. So maybe because of changing environments or maybe because of some privacy concerns, our data may have some bias. So we need to somehow debias data or debias our predictors. Or we suffer insufficient information. Maybe our data does not contain really information fully, but it only contains weak supervision. But still we want to train our predictor. Or label noise is quite critical nowadays because many big data are collected by human or sensors. Then we have a lot of errors. Then finally, attacks. So we may suffer adversarial noise or adversarial distribution shift. So we need to somehow cope with these attacks. So in this talk, so I will give an overview of our recent research on these topics. But because time is limited, I try to focus on the first 2 issues. So data bias and insufficient information. Okay, so first, let me start from transfer learning, so data bias part. So let's consider the situation where training and test data have different distributions. So this is often not really avoidable because of changing environments. Maybe over time, our environment is changing. So in training and test phases, our data distributions may be different. Or sample selection bias. Like we want to collect data in a uniform way, but because of some privacy concerns, we are allowed to take only a small portion of data from some biased population. So transfer learning or domain adaptation is to tackle this issue. So we try to train a test domain predictor using training data from different domains. So actually, we have been working on this topic for long years. So like in NIPS 2006, actually we organized a workshop called Workshop on Learning when Test and Training Inputs Have Different Distributions. Then after that, we edited the volume like this. And also we wrote a book on covariate shift adaptation already about 10 years ago. But we are still continuing this line of research because we had some nice progress recently. Okay, so let's formally set up the problem. So for training a classifier, we are given training data. So they are IID samples from P training of X and Y. So X is input and Y is output. So then our goal is to train a predictor f of X. That works well even in the test domain. And in reality, we need some additional data from the test domain, like unlabeled data or some validation data, depending on the methods setups. So I will talk about it later. But given training data and some additional information, we want to train a predictor F that minimizes the test risk, R of F. And test risk is defined as the expected loss over PTE. So training data is from PTR, but test data is coming from PTE. And we want to minimize this expectation over PTE. So clearly the challenge is to overcome this changing distribution. So in this transfer learning setup, we have actually various scenarios. And the most general one is full distribution shift. So PTR of X and Y. So joint distribution, joint densities change between training and testing in an arbitrary way. So this is the hardest situation. But we have a lot of special cases. And sometimes these are more useful in practice. For example, in the case of covariate shift. So covariate is the name for input X. So covariate distribution, X distribution change. Like PTR of X is different from PTE of X. Or class prior shift or target shift. So P of Y changes between training and testing. Or output noise or label noise, P of Y given X changes. Or class conditional shift, P of X given Y changes. So we have many different scenarios. And today I focus on the first two issues. So full distribution shift and covariate shift. And let me start from covariate shift and introduce some basics. So let's consider the covariate shift scenario. So this was actually the term covariate shift was coined by Shimodaira in this paper, 2000, more than 20 years ago. So the training and test input distributions are different. PTR of X is different from PTE of X. But the Y given X, so output given input distribution remains unchanged between training and testing. So then in the case of regression, this is basically a kind of extrapolation problem. Like let's say, so training input density is this Gaussian at around 1. And test input density is this black Gaussian around 2. Then 1 and 2 here. Then there's a target function for regression. And P of Y given X does not change, basically means the regression function does not change, but only input distribution changes. So this basically means in the training phase, we have training input points from this blue Gaussian, so points around 1. So we have blue points like this. Then in the test phase, we will have test points at around 2. So black points here, black crosses here. So the given blue points, we want to make prediction of black crosses. So this is the covariate shift adaptation problem. So it's an extrapolation problem and extremely challenging. So then for learning, so the most fundamental approach is empirical risk minimization. So we consider the empirical loss for training data like this. Then suppose we have a straight line model, AX plus B. If we perform empirical risk minimization, maybe by squared loss, it's just least squares fitting like this. So we are fitting blue points nicely. So this is the result of empirical risk minimization under covariate shift. So generally, ERM is statistically consistent. This means that the learned function converges to the optimal solution when the number of training data goes to infinity. But as you can see here, so this green line does not really converge to the optimal solution that predicts black crosses quite well. This is because of covariate shift. So it makes ERM inconsistent. So if we take the limit, this converges to the expectation over PTR. And this PTR is different from PTE. So that's why we have inconsistency. Then to overcome this problem, the importance weighted version of empirical risk minimization was proposed. So here we have PTE of X over PTR of X. So this is called the importance weight or importance ratio or something like that. Then surprisingly, so applying this importance weight, if we train a classifier from blue points, a regressor from blue points, then we have this green line. So we are fitting blue points, but we obtain this green line that predicts black process quite well. So indeed, this importance weighted ERM is statistically consistent, even under covariate shift. So this is because now this term, the product of these two converge to the expectation over PTR. Then this PTR and this PTR in the denominator cancels, and we end up having PTE here. Then this is the test risk. So if we have a large number of training points, then this importance weighted ERM converges to the optimal solution. So that's the good news. But how can we know the importance weight? So this is usually unknown because we are only given training data. So this is a problem of importance weight estimation. And here, let me quote Vapnik's principle from his famous book. So when solving a problem of interest, one should not solve a more general problem as an intermediate step. So let's apply this principle to this importance weight estimation. So if we know two densities, this is Y, so PTE of Y and X is fine. So sorry, this is fine. So this is, if we know two densities, then taking the ratio can, compute the importance weight, but not other way around. If we can estimate the ratio directly, we cannot decompose them into two densities uniquely. This basically means that estimating the ratio is substantially easier than estimating the densities, both densities. So that means we should solve the right-hand side problem, so knowing the ratio. So this is called direct density ratio estimation. And we have been working on this topic for long years, and already we had a book on this about 10 years ago. So there are many nice methods. And let me just briefly review one of the simplest methods called least squares importance fitting. So in this setup, we are given training and test input data, so XTR and XTE. And from these two sets of data, so we directly fit a density ratio model R to the true ratio PTE over PTR by least squares. So this basically means we consider R minus R squared and try to minimize it with respect to R. So because R star is unknown, this is not really solvable at a glance. But if we expand the squared term, then we end up having R squared here, R squared PTR here, then two terms R star PTR. But because R star has PTR in the denominator, so these two are cancelled, and we only have 2 times R PTE. Then finally, we have R squared PTE, but this is constant with respect to R, so we can ignore it. Then the first term is basically the expectation of R squared over PTR. And the second term is basically the expectation of R over PTE. So then we can empirically approximate them by these two samples, two sets of samples like this. So this is computable and we can minimize it. In particular, if we have a linear imparameter model for R, so we can solve the optimization problem analytically. So it's quite efficient. So then given those methods, the classical approaches to solve the covariate shift problem is 2 steps in nature. First, we estimate importance weight by least squares importance fitting method that I just reviewed like this. So once R hat is obtained, we train a predictor based on importance weighted empirical risk minimization. And instead of true R, we have R hat here. Then we hope that F hat is a good solution. But here the question is, so can we integrate these 2 steps in a single shot? Because solving a problem in 2 steps is actually not the best. because when we estimate the importance weight R, so we don't really care the second step. So maybe the estimation error in R could be magnified in the second step. So ideally, we should solve these two problems simultaneously. Already, I had the motivation to integrate these two steps. So maybe more than 10 years ago, but I didn't have good ideas yet. But finally, recently, we had a nice progress along this line. So one method is called joint upper bound minimization. So suppose we are given labeled training data and unlabeled test data. So this is the standard covariate shift adaptation setup. Either it's semi-supervised learning or unsupervised domain adaptation or something like that. Then we want to minimize the test risk. So it's the same. So we have loss function L here. And to solve the problem, actually, we consider two loss functions. So one is L, so used in defining the risk function. And we assume that it's upper bounded by 1. So as long as it is bounded, we can always normalize it to 1. But we are not allowed to use unbounded loss function. And also L prime. So this is a surrogate loss that we use in training. And assume that this L prime is larger than or equal to L. So it's an upper bound of the original evaluation loss. So this is a bit complicated, but in the case of classification, L is a 0-1 loss. Maybe this is almost always the case. Then as L prime, we may consider the hinge loss for binary classification, or for multiclass case, we may consider softmax cross entropy. So these satisfy these conditions. But in the case of regression, we want to use the squared loss usually, but we are not allowed to use it because it's unbounded. So instead, we consider the 2-key loss, L. So it's upper bound, it's just normalized and it's upper bounded by 1 like this. And then as L prime, we use the squared loss. Then, so for training, we can use L prime as usual. So then, okay, given such L and L prime, and we assume that the importance weight R is lower bounded by 0, non-negative, then the test risk R is upper bounded in this way. To be precise, the test risk squared and divided by 2 is upper bounded by this J. And surprisingly, J consists of 2 terms, and the first term is actually exactly the same as importance weighted empirical risk minimization with L prime, but it's squared. Then the second term is exactly the same as the least squares importance fitting criterion. So this is quite interesting. So given this upper bound, actually the 2-step approach. So first solve LSIF and then perform IWERM. So this is basically a kind of successive minimization of the single upper bound. So this is clearly not optimal. So we should definitely optimize this J, minimize this J directly with respect to both R and F. That should minimize the upper bound. Okay, then, so for this method, so under some mild conditions, the test risk of the empirical solution. So now J hat is what I showed here. So empirical version. And if we minimize this with respect to F and R, and let's say it's F hat, then the test risk of F hat is upper bounded in this way. So this is the test risk measured with L prime. So this should be small enough to guarantee that our method works well. But other than that, so it converges nicely. Although its convergence rate is not optimal because we took the risk squared when we derive an upper bound. But still, so this is a kind of guarantee for our 1-step method. Okay, then, so in practice, this is implemented in this way. So importance weighted is learned and predictor is learned, and this is repeated. So it's a joint optimization, but it is basically successfully, alternately minimized. Then for some benchmark data sets, so plain empirical risk minimization does not work. And if we use a traditional method, it reasonably works well sometimes, but sometimes it does not work well. But then, so we had the previous best method here, but our 1-step joint method actually outperforms the previous best method in this way. So this is the one-step approach for covariate shift adaptation. Okay, then so let me introduce one more method called dynamic importance weighting. This is actually also quite interesting and very simple approach. So now let's consider deep learning. So deep learning usually adopt stochastic optimization, stochastic gradient descent. So function is updated by following the gradient like this. So in this scenario, so let's learn importance weight R and predictor F dynamically in the mini-batch wise manner. Because now the training is done in a mini-batch way. So we try to learn R and F dynamically in this stochastic optimization process. So it goes in this way. So now we suppose that we have label data both from training and test domains. So it's not a semi-supervised learning anymore, but we assume that we have some like validation data from the test domain, label data. We suppose it's small, but still we should be able to access this label test data. Then once we accept this setting, then for each mini batch, so some subset of training data and some subset of test data, so importance weights are estimated by kernel mean matching for loss function. So this means that we have loss function for the training data here and importance weight Ri here. This should be approximately matched to the test loss, average test loss from the mini batch. So maybe this approximation is quite crude because the size of mini batch is usually small, but this is only like one step in stochastic optimization. So it's not actually a big issue as long as we can roughly find a reasonable direction for optimization, gradient direction for optimization. And more importantly, so in this discussion, no covariate shift assumption is needed. This means that basically full distribution change is allowed in this optimization, in this adaptation method. So it's a very simple method. So we just have loss value for training and validation data and apply kernel mean matching to obtain the importance weight. Then train the classifier and like that, just update it. So then, under some setup, so this dynamic importance weighting method seems to work quite promisingly. So implementation is quite simple and it's also working quite well. Okay, that was the first part of my talk about transfer learning. Then the second part is weakly supervised classification. So machine learning from big label data is quite successful in like speech recognition, image understanding, language translation, or online advertisement, etc. An estimation error of the decision boundary may decrease in the order of 1 over square root of n, where n is the number of label data. So that's why we want to have big data. But unfortunately, in other applications, so label big data is not really available. Like if we work on some medical problems or natural disasters, robot control, brain data analysis, once human is involved, then collecting big data is quite impossible. Or if nature is a target, also collecting label data is quite hard. So in that kind of case, we may want to rely on unsupervised learning, unsupervised classification. So here we don't use any labels, so that's quite easy to use. But basically, unsupervised classification is just clustering. So we just split the data into clusters. Then, so if we use it for classification, basically there's no guarantee for prediction. So by chance, if one cluster corresponds to one class, maybe our performance is quite good, like MNIST dataset or USPS dataset, but usually not. Then to overcome the problem of unsupervised classification, people prefer to use semi-supervised classification. So we try to additionally use a small amount of label data, like one positive point here and one negative point here. Then we propagate labels along clusters like this. So this is a simple and nice method, but again, no guarantee for prediction unless we have a certain cluster assumption. So then to cope with the labeling cost, we can consider several different approaches. For example, we may simply improve the data collection process based on by using crowdsourcing. Well, we may use a simulator to generate pseudo data, like in physics, chemistry, robotics, etc. Or in companies, so they try to use their domain knowledge and tuning to improve the performance. Or finally, so we may use cheap data, but weak data. Unlabeled data is one of the examples, but we may consider many other variations. So this is weakly supervised learning. So once we take the classification accuracy on the horizontal axis and labeling cost on the vertical axis, then supervised classification is most accurate but most costly. Then unsupervised classification is the cheapest but lowest accuracy, no guarantee. Then semi-supervised learning is also located somewhere here. So the target of weakly supervised learning is basically this bottom right corner. So we try to achieve high accuracy and low labeling cost at the same time. So this is the challenge of weakly supervised learning research. Okay, then so let me first talk about positive unlabeled classification. So that's basically the basis of weakly supervised classification research in our team. So in this PU classification, we have positive data and unlabeled data. So P data is coming from P of X given Y equals +1. And U data is coming from P of X, so marginal density. And from PU data, we try to obtain a PN classifier, positive negative classifier, a standard one like this. So actually there are negative points here, but they are not observed. So we only observe blue positive points and also unlabeled, black unlabeled points like this. And a motivation to consider this PU classification is, for example, click prediction. So we can actually easily collect clicked links. So those are the ones user like. So they are positive data. And similarly, we can easily collect unclicked ads or unclicked links. But we can't really determine whether users don't like these unclicked ads or users actually like those unclicked ads, but they didn't have time to click them. So from that viewpoint, unclicked ads are basically unlabeled data. So they can be either positive or negative. So in this kind of scenario, we naturally have only positive and unlabeled data and no negative data. So that's the setup of PU classification. Then how can we solve this problem? So again, let's consider the classification risk. So L is some loss function, and we consider L expected over PXY. So this is a classification risk that we want to minimize. Then this can be naturally decomposed into the risk for positive data and risk for negative data. And if you have positive data and negative data, then these two risks can be estimated from samples easily. But in PU classification, we only have positive data and unlabeled data. So the first term can be easily estimated, but the second term cannot because we don't have negative data. Then one thing I must say that, so we have pi and 1 minus pi here. So these are class prior probability. So P of Y equals +1. So today in this talk, I assume this is known, but in practice, we should estimate pi also from PU data. But luckily, already there are several nice methods to estimate pi from PU data. Although I must say that this problem is not still completely solved yet. There are some open issues, but already there are some methods. So today I assume pi is known, but still there's some issue here, I must admit. Okay, so then let's come back here and let's focus on this risk for negative data. And we try to estimate this only from PU data. So that's a technical challenge here. But this is actually quite simple. So we know that P of X, so this is density for unlabeled data, is a mixture of positive density and negative densities. So suppose we have positive class density, blue one here, and then negative class density, red one here. Then, so marginal density is basically a mixture of these blue one and red one with proportion pi and 1 minus pi, like this black dotted line. So let's use this. So we have unlabeled data. So then basically P is kind of estimable, accessible. And we have positive data, then this P of X given Y equals +1 is estimable, accessible. So then unknown, this negative density can be basically estimated by Px minus pi of P of X given Y equals +1. So that's the basic idea. We plug this relation into this part. Then we can basically eliminate the negative density, but instead we have P minus this term, positive density. So that's the tree, whole tree. Now we can replace these three expectations by sample averages because we have positive data, unlabeled data, and positive data. Then naively we can obtain an empirical risk like this. So that's the solution. So if we minimize this, we can obtain a solution. And also we can prove that, so minimizing this is actually optimal. So the convergence rate is 1/square root of NP and 1/square root of NU. So this is the optimal parametric rate. And also one important and interesting finding is that, so we can actually compare the estimation error bounds for PU learning and PN learning. So the first line is the same as the previous page. We had the bound like this. And with a similar proof technique, we can also have an estimation error bound for standard supervised learning, PN learning. And actually upper bounds are quite similar and C is actually common. And actually we can compare these two upper bounds. So then actually PU upper bound is smaller than this PN upper bound if this condition is satisfied. I just compared these two terms. So this basically means if we have a large number of positive data or a large number of unlabeled data, then this inequality tends to be satisfied. If we only have small number of negative data, then this inequality tends to be satisfied. So it's actually surprising because PU learning is a kind of compromise. If we have PN data, so that's the best. But because M data is not available, we decided to use U data instead. So the starting point was a compromise. But it turned out that so PU learning can be actually better than PN learning if this condition is satisfied. So this means that if we only have a small number of negative data, but a large number of unlabeled data, then actually we recommend you to use PU learning because this relation tends to be satisfied. Then PU actually gives a better solution than PN. Okay, that's a story so far, but we need actually one more issue. So what we have done so far was, so we decompose the risk into P risk and N risk. So let's write R minus here for the N risk. Then we use this relation. So marginal density is a mixture of positive and negative densities. And we plug this one to eliminate this negative density like this. Actually, we have minus here. Suppose the loss function is now non-negative. Then, so by definition of this R minus, it is non-negative because we just take the expectation of a non-negative quantity. But in reality, we approximate this R minus from PU samples like this. Then, so its PU empirical approximation can be negative because of this difference of approximations. Like let's say originally it was 3 minus 2, so it's 1, so non-negative. But now 3 is unknown, so it's estimated. So 2 is unknown, it's estimated. Then sometimes maybe 3 becomes 2 and 2 becomes 4 or something like that. Then so it's 2 minus 4, then minus 2. So because of this difference of approximations, so non-negative term becomes negative in this PU learning formulation. And unfortunately, this negative problem is more critical for flexible models such as deep neural networks. So let's see a numerical example. So horizontal axis is the stochastic gradient iterations. And suppose we just perform back propagation using positive negative data in the usual way. Then as blue dotted line shows, so training error decreases nicely over iterations. Then at the same time, test error also decreases nicely, blue solid line like this. So that's a standard situation. But in the case of PU learning, so over stochastic gradient iterations, training error decreases again nicely, but at this point, it becomes non-negative like this, and it goes negative like this. Then interestingly, the test error actually started to grow like this. So it's a clear phenomenon of overfitting. So we want to avoid this problem. So our solution is to constrain the sample approximation term to be non-negative. like we had 3 terms, and last 2 terms are coming from the negative part. So we just had max 0 here. So once this term becomes 0 and negative, we round it up to 0. So this is our like modified estimator, risk estimator. So then, so this is actually biased because of this rounding up operation. So we should confirm whether this is really a good modification. So we had some theoretical analysis. This modified version, R tilde, is luckily still consistent. So meaning that if we have infinitely many points, so this R tilde converges to the true risk. And its bias actually decreases exponentially fast, like this. So this practically means we can ignore the bias. It is biased, but its bias is quite small. And also the mean squared error of this R tilde is not more than the original one because of this max 0 operation. So that means in practice, this R tilde is more reliable than the original one. Then finally, the risk of this R tilde minimizer for linear models attains the optimal convergence rate like this. So then perhaps the learned function is still useful in practice. Then so we tried to implement this idea in a simple way for deep learning. So instead of taking max 0 operation, so we had a slightly different implementation. So again, so we used the standard mini batch stochastic gradient optimization for deep learning. Then if this R hat minus is non-negative, then so we don't suffer this max 0 issue, and we just perform standard gradient descent as usual. But if this term becomes negative, then actually we decided to perform gradient ascent. So going back. Actually, this is because, so if this term becomes negative, then our mini batch data is actually quite bad. So that means so we may have overfitting in them. To avoid it, we decided to step back the gradient to avoid converging to a poor local optimum, because the optimization landscape is quite complex in deep learning, and there are a lot of poor local optima here and there. And maybe if we just follow the gradient when this R hat is negative, we may end up in converging to a poor local optimum. To avoid the risk, we go back and recompute the gradient with a new mini batch of data and hope that we have some randomness and go to another direction to find a better optimum, local optimum. So that's our practical implementation. Then, so we did experiments. Then, so we had actually similar results. So for PN learning, so blue line, so dotted line is a training error, so it converges to 0 nicely. Then for test data, so it converges like this. It works reasonably well. Then without any non-negative correction, the PU training error decreases quite fast and go to negative like this. Then the test error go down and increase like this. But once we have this non-negative correction, then the training error decreases nicely and kept non-zero, non-negative like this. Then the test error is also kept small like this. And it's interesting to see that this yellow final result, non-negative PU test, is actually smaller than PN test. Actually, in this case, we assumed a large number of unlabeled data. Then the condition that I showed in the bound was satisfied. Then PU is expected to be better than PN. And it really happened in this benchmark data, CFAT benchmark experiment. So that's a kind of surprising result, because we can outperform PN only from PU data. Okay, so then summary of this weekly supervised learning PU classification part. So we basically proposed a risk rewriting technique. So we first defined the classification risk like this, and then we rewrote the classification risk only in terms of weak data. Like in the case of PU learning, we expressed this classification risk only in terms of positive and unlabeled data. So then this is still a standard empirical risk minimization formulation. So we can easily guarantee optimal convergence. And also, because of this generality, our methods are basically compatible with any loss function or any regularizer or any model like neural networks, a linear model or support vector machine, and also any optimizer. Then finally, I will show in the next slide. So this idea, this risk rewriting is applicable to various weak data, not only PU learning. The one more important finding was non-negative risk correction. So this was actually really necessary for weakly supervised classification. So we tried to utilize intrinsic non-negativity to mitigate overfitting. So this overfitting is not coming from simply like small sample effect, but it's an intrinsic problem. So non-negativity of loss or convexity can be actually utilized to have some non-negativity constraint. And again, it can be applied to various weak data and also applicable to noisy label learning. So today I don't cover this, but this non-negative correction technique is quite general. Okay, then so let's go to the next part and let's talk about extensions of this weakly supervised classification briefly. So I have already talked about PU learning, so it can be applied to click prediction or something like that. Then based on this PU learning, actually we can have another semi-supervised classification technique that we call PU plus PN. So we basically combine PU learning and PN learning to use all positive, negative, unlabeled data. Then, so surprisingly, we can actually theoretically guarantee that so unlabeled data really helps in this PU plus PN learning. So to the best of my knowledge, this is the kind of fast theoretically guaranteed method for general semi-supervised setup. Then, so in PU learning, we used positive and unlabeled data, but we tried to solve it only from P data. But only P learning is not possible because it's unsupervised, same as unsupervised. But we found that positive confidence data is sufficient. Like we know, if we know this point is 95% positive or 20% positive or like that. So this is possible in purchase prediction where unlabeled data is not available from rival companies. Or similar dissimilar classification is also important extension. So suppose we consider delicate information classification, like about your salary or about your religion, then it's not easy to collect yes/no labels directly. But we may have similarity or dissimilarity information. Like, okay, my answer is same as that person, or his answer is different from that person's answer, like that. From these similar dissimilar data, again, we can train the classifier. Then finally, so more generally, okay, we can solve a classification problem from two sets of unlabeled data. Like suppose we collect data from two different hospitals and assume that the population of patients are different in two hospitals. Then surprisingly, from these two sets of unlabeled data, okay, we can obtain a classification boundary like this. And this UU classification actually contains PU and ST classification as a special case. So it's actually a very general framework. And furthermore, we can extend the idea to multi-class classification. Maybe that's more important in practice. And risk rewriting is still possible in multi-class problems. I don't really go into the detail, but we consider several different scenarios, like complementary labels. So usually, so ordinary label specifies a class that a pattern belongs to. Like this sample belongs to class 2, or this image contains dog or something like that. But complementary label specifies a class that a pattern does not belong to. Like this sample does not belong to class 3, or this image does not contain dog or something like that. So only from those not labels, complementary labels, we can solve a classification. We can estimate the classification risk. And similarly, partial labels specify a subset of classes that contains the correct one. Like either this sample belongs to class 1 or 2, or this image contains person or dog or something like that, or label. But still, we can estimate the classification risk only from partial labels. And the single class confidence is also possible. So we only have data from one class, but one class data is equipped with full confidence. Like class 1 with 60%, class 2 with 30%, class 3 with 10% or something like that. Then again, we can solve the classification problem optimally. So all methods can achieve one over square root of n convergence. Okay, so altogether, so this is the kind of empirical risk minimization framework for weakly supervised learning. And we try to cover this area, bottom right corner. So all our empirical risk minimization. So then in principle, we can combine all weak supervision. So PNU, ST, PConf, NConf, SConf, DConf. So for binary problems, we can combine all of them. And all of them can join estimating the empirical risk, classification risk. So now, so we decided to write a book on this topic a couple of years ago. And then finally it was done, and already the manuscript was in the publisher. And hopefully this book, Machine Learning from Weak Supervision, will appear quite soon from MIT Press. Okay, then future outlook. So let me spend a few more minutes. So today's focus was reliable machine learning. So then the approaches basically today was reliability for expectable situations. So this means that we try to model the corruption process explicitly and correct the solution. Like weakly supervised learning and transfer learning, we had the kind of model behind, and we followed that model. Then a natural question is how to handle the modeling error. Like we assume covariate shift, but maybe the target distribution may slightly change or something like that. We need to somehow cope with that kind of modeling error. And another completely different approach is opposite approach would be the reliability for unexpected situations. Like we don't really assume anything. So then the worst case robustness is the standard approach or minimax approach. But many of us know that minimax approach is quite conservative because the worst case is really the worst case. That doesn't happen in reality. Then coping with that kind of worst case is really not at all useful in practice. So how to make it less conservative is an important challenge along this line. Or if we faced with unexpected situations, then we may ask human to help, like a classification with rejection. So this is also possible. But this cannot be applied to handle like real-time applications like autonomous driving. Like medical diagnosis is fine, maybe if there's a patient image, medical image, and it's not clear whether cancer is included or not. We can simply ask professional medical doctor to check it. But in the case of autonomous driving, so car is running and human is not really driving, then it's not possible to ask human to control the car and drive the car anymore. So that's another issue to be discussed. But in practice, perhaps the situation between these two would be quite important. We may use partial knowledge of the corruption process to somehow cope with unexpected situations. So still, I don't really have a concrete idea how to approach this problem, but I'm interested in this direction now. So then about our way of doing machine learning research, so briefly. So we actually try to decompose machine learning research into conceptually orthogonal topics, like modeling issue or learning methods or regularizers or optimizers, etc. Like in today's case, actually, we had that basically two axes, so model and learning method. So along the learning method axis, we have supervised learning, unsupervised learning, semi-supervised, weakly supervised, or even reinforcement or transfer, adversarial, knowledge robust, or whatever. So these are basically learning methods. And this is conceptually orthogonal to models like linear model, additive model, kernel model, deep model, or whatever, more complex models. So then this actually decomposition is quite useful in terms of doing research, because model research is quite active and you can find new papers in arXiv almost every day. So it's impossible to catch up with the latest papers. But once the concept is orthogonal, we can basically ignore this axis when we do research. So just develop along this axis, learning method. Then once a certain method is created, we combine that method with the latest model. Or if we want to analyze the method theoretically, we may choose the simplest linear model. So the combination is arbitrary. And same goes for regularizers and optimizers. So this kind of decomposition would be quite useful in conducting machine learning research. Then, so slight technical issues that we had breakthroughs recently. It's not that big issue, but it's quite important in our research. Because classical convex learning, like support vector machine, allowed us to analyze the global solution because of this complexity. But in this deep learning era, optimization is complex, and we just use stochastic gradient to find a local optimum, or maybe some global optimum. Then the difference is that, so thanks to this gradual learning nature in deep learning, we can actually utilize intermediate learning results. So previously, when we worked on support vector machine, we only looked at the final solution. But in the case of deep learning, we can see the intermediate result, and we can actually update our learning objective. So this idea was already utilized in like weakly supervised learning, or transfer learning, or noise robust learning. So that's actually quite interesting and useful to really tackle a challenging problem. Okay, thank you very much. That's the end of the talk today.
Fantastic talk, Masashi. I learned quite a bit from this talk, and I hope that we can actually open these travels next year. Hopefully the situation will improve. Thank you very much for this. So there are several questions in the Q&A. I think that maybe we can go over them. If let me know if you could see them.
So, okay, we have some in chat window.
So I think we refer to them to go to Q&A.
Q&A, okay. So,
yes, so okay. I would recommend maybe starting with the Q&A.
Okay, so under covariate shift, so because PTRX is very small, the ratio is susceptible to noise. So I think the ratio estimation is not necessarily easier than estimation of both. So, okay, so if the ratio is quite fluctuated, yes, it is difficult. But in that case, density estimation is even more difficult. And taking the ratio of two estimated quantity is really, really bad. So I can't really say that directly estimating the ratio can really solve such a difficult problem. But still, it is relatively better. But already we have shown one-step approach today. And in the one-step approach, actually, we don't really estimate the importance ratio as it is. Maybe it's quite fluctuated. But in the one-step case, we are actually automatically finding a kind of nicely smooth one to really minimize the generalization error. So conceptually, I think we have already addressed your question today. So thank you very much. So then the next question is, so why do you take square of IWERM of the joint upper bound minimization? So even without the square, it is still an unbiased estimate of the risk. So, okay. So one technical reason would be, so in the importance weighted empirical risk minimization, we have importance weight, but we use squared loss for the importance weight. Then R squared appears. To have R squared, we just square the risk. So that's a kind of reason we had to take the square of the risk to derive an upper bound. But still, it's just one of the activities. Hopefully we can hopefully we can have another good way to have an upper bound so that the convergence rate can be optimal. So it's great if we can have more discussion on this later offline. Thank you very much. So then the next one, so could this weakly supervised learning method used to solve the attributed based interoperation problem? The attribute that contributes the interpretation is more like the P in the U. So we try to find that the P that really helps interpretation. So okay, so that's a very interesting question. So still, it's not clear what do you mean by interpretation here. But now we can somehow select P from U data. Then, so once we have another criterion in terms of interpretation, then we should be able to do something. But it's slightly outside the current weakly supervised learning framework. So maybe, again, we can have some discussion to how to incorporate this interpretation criterion into this framework. Okay, then so next question is, why is the training error for deep learning negative? So, okay, that was something we have shown already. So because we don't have negative data in PU learning, we try to estimate the error loss for negative data only from positive data and unlabeled data. or more specifically, unlabeled data minus positive data is a kind of negative data. So because of this minus operation, so empirical risks sometimes go to negative. And this is a kind of overfitting issue. So once we have a very flexible model like deep learning, then all data points can be exactly memorized. Then actually the training error goes to negative. We can really show that. So that's why we need this is an intrinsic problem for weakly supervised learning for deep models, and we had a non-negative correction so far. Okay, the next question is, conceptually, error is the difference between the ground truth and estimated value. Yes, which cannot be negative. So what does negative error suggest? So again, the true error is non-negative, but we can't access the true error, and we try to estimate the error from empirical data. So in that case, we have some estimation error, and this estimation error causes the estimate to be negative. So this is how we had the negative error, and we gave a systematic method to correct it. Then what is the difference between simple clustering and UU problem? Okay, simple clustering is clustering from one set of unlabeled data. But in UU problem, we have two sets of unlabeled data. And also we need an assumption that class priors are different in these two sets. So actually UU classification problem can be regarded as like noisy label classification problem. Like we have two unlabeled data sets, and one is regarded as noisy positive data set, and the other is regarded as noisy negative data set. So that's why actually we can solve PN classification problem from two sets of unlabeled data. Okay, about slide 39, do you have an idea why the non-negative PU test shows lower than the PN test? So this is what our theory predicted. So if we have like in PU learning, we only use positive data and unlabeled data. And PN learning use positive data and negative data. And suppose we have a large number of unlabeled data and small number of negative data. Then, so maybe it's intuitive that using PU is better than PN, because we have a large number of U data and only small number of N data. So that's why PU can be better than PN. But in reality, actually, we should combine both of them. So as I shown somewhere, so PU plus PN learning. So this is a semi-supervised classification. This is actually better than PU and better than PN, because we use all PNU information. And also, like we can basically combine all information, as I said somewhere. So if you have some pconf data or sconf data or whatever, so we can actually use any piece of information to improve the classification error. So that's a kind of generality of empirical risk minimization framework. Then dynamic importance weighting seems to perform poorly on dataset with many classes. Is there a reasoning for this? Can this be improved, say, label smoothing? Yeah, label smooth. So, okay, many class problem is always very challenging. And not only dynamic importance weighting, but for any methods, this is challenging. And in general, so label smoothing must be useful if you have some nice knowledge on like a relation between labels. But still, it's completely open in this dynamic, in the context of dynamic importance weighting. So if you have any ideas, I'm happy to have more discussion with you. Thank you very much. So then, is it true that multi-class weak labels method improves robustness for classification? Okay, so robustness. So the meaning of robustness is a bit unclear in my presentation today, because it was more like a title of the talk. But okay, we are simply saying that we can achieve the optimal convergence rate only from weakly labeled data, as if we have fully supervised data. So that's how we compensated for the lack of supervision to be robust against weak supervision. So maybe from that viewpoint, my answer should be yes. It is possible that so multi-class weak labels method improves the robustness. But if you talk about noise, maybe that's a bit another story. And we have no answer to that question yet, unfortunately. Then is Gaussian distribution assumed for all cases? Basically, no. So we don't have any assumption on distributions at all. So any distribution is fine, except for some very technical issues. So no Gaussian sampling is needed. And does multi-class method work for the case where the number of classes are unknown? This is a challenging problem. So far, we just consider the standard multi-class problem. So we have C classes, and we just solve the C class classification problem. But in the scenario where a new class appears, so maybe that's another important challenge. So that's still open in this context. But I hope this is conceptually orthogonal again. So we may be able to combine some of the new class problem, new class method into our current framework. Then adversarial attack is quite related to distribution shift. So what is your opinion about their relations? Maybe adversarial attacks may contain different types. So the changing input point is maybe standard one, like changing the image or pixels. So that's a standard one. But also changing the distribution is another way of attacking the system. So maybe not only these two, but there must be a lot of different attacks that go beyond our imagination. And this is actually the challenge here, right? So we try to develop a protection method, defense method, given some certain type of attack. So this is always important. But attackers are always going fast, and they try to develop something new. Then so defenders are basically following attackers, and this is really a bad endless game. And this is happening already in the computer security field. A defense method appears, then a new attack appears. So that's a big headache. So we need to somehow go beyond this bad loop. So that's my current feeling. So are there any way to transfer the model to other feature distributions? Feature distributions means X, right? P of X. What other types of modal data can? Okay, so you have new features. Yeah, that's an interesting question. So suppose we have some new features. So can we utilize that to improve the performance? Yeah, that sounds a very interesting and challenging problem. So I don't have an answer yet, but again, hopefully that problem is conceptually orthogonal to the weekly supervised results. Then we can combine the latest results from both fields.
It's also related to domain generalization, I believe.
Right. True. So then in batch-wise learning, so why we consider only average? We can consider median or other stat parameters, right? So to make things robust, so clearly taking the average is the worst thing. So we can consider median or some other and trimmed mean or whatever, more robust statistics. So another question is, so this is a bit long question, and sorry that I can't really digest it immediately. So maybe offline I try to read it and maybe try to answer your question later. Or maybe if you could send me an email, maybe we can have a bit more discussion later offline. And the last one, so you assume the simple linear combination of positive and negative densities. Does your framework hold true for more complex px density, such as nonlinear combination of two? I'm not quite sure, because that decomposition is coming naturally. So we assumed p of xy, so joint distribution behind. Then it's just marginalization. So then we have sum of two densities, positive densities and negative densities. Then from that viewpoint, there's no way to consider more complex nonlinear combination of these two. But maybe I'm missing something. If there is a possibility that nonlinear combination makes sense, that would be, I think, quite new and interesting problem. Okay, great. So now 10 minutes over. So thank you very much for joining the talk today. So then next week, we have talk by Taiji Suzuki on learning theory. So we will continue this seminar. So next week and in 2 weeks this month. Then after that, we have a little bit more sparse, but we continue this series for, I don't know, half a year or quite long if possible.
Thank you, Masashi, for this great talk. I was also going to say, look forward to Taiji Suzuki's talk next week. And then the following week, Nicolas Flammarion from EPFL will give a talk. Thank you again, Masashi.
Yeah, thank you very much. And thanks for joining today.